Hello again. I'm Professor Norton from WPI, and today I'm going to show you how to construct a single dwell mechanism using only pin-jointed linkages. First of all, I'll define a dwell as a period of stasis, which is to say no motion of an output link while the input motion continues. These are very commonly used in various kinds of machinery, either to allow the loading or delivery of a part. You want to keep the end effector stationary for a short time, or to allow other events to complete in the cycle. The easiest way to achieve a dwell is with a cam and follower, and its dwell can be exact. And in fact, most, if not all, of the applications that you typically see in machinery do in fact use cams and followers. You might wonder why we're bothering with this. Well, I think it's useful for you as a kinematician to understand that you can get a dwell from a linkage with no cam joint, which has some advantages. But unfortunately, you can't get an exact dwell, only an approximate dwell with this approach that I'm going to show you. We are going to have at least 6 links to get a dwell mechanism, a dwell motion. We're going to use a 4-bar linkage as the basic building block, the basic driver, and we'll look for a Grashof 4-bar with a coupler curve of a particular shape, and we'll make that drive an output dyad, or 2 more links, giving us the 6 links, and then we'll end up with a Stevenson 6-bar when we're done. And we're going to be looking for a coupler curve that has either an approximate circular arc segment or an approximate straight line segment. Now, you should know from your readings or from viewing the tape on coupler curves as part of this sequence that you can get approximate straight lines with a 4-bar, but you can't get an exact straight line. You can also get approximate circular arcs, and in fact you can get an exact circular arc at certain coupler points, but those will not be of value to us here. There are 2 methods shown in the book, one of which uses the circular arc and the other the straight line. I'm just going to use the circular arc here. And we need that arc or line piece of the coupler curve to be of sufficient duration in terms of the input crank angle to satisfy our dwell. So if we wanted 60 degrees worth of dwell, we'd need 60 degrees of motion of the crank of our Grashof linkage to give us the circular arc portion. That should become more clear when I do an example shortly. This is a figure from your book and shows the approach. So I'm giving you a little preview of what I'm going to do momentarily in actual construction here. Here's a Grashof 4-bar, which generates this coupler curve, and it has a portion which is approximately arc-shaped, and that portion, shaded here, represents a certain rotation angle on the part of the crank, let's say 60 degrees. We're going to take that coupler curve and use that point, P, to drive another pair of links, the so-called output dyad, and those are shown over here. So in this diagram, the 3 moving links that are generating that coupler curve have been removed from the picture so as not to clutter things up, and you're looking only at the coupler curve generated by this linkage over here, and that portion of the curve which is arc-like is outlined in red. So if we can find the center of that approximate arc, which is down here at D, we can do that with some simple construction. If we then place a link from P to D, I think you can picture that as this end of the black link labeled 5 moves along the arc, this end D wouldn't move at all if that were a perfect arc, and it'll move only a slight amount if this is an approximate arc. So that's the trick. We're going to get this end of D to be more or less stationary while the other end at P traverses this part of the curve. But when P continues around this part of the curve, D will move down to some new location. So if we attach a 6th link, here labeled link 6, with some pivot of convenient choice, some convenient location, I can end up with some kind of a swing motion on the part of link 6, which will occur only during the time that this point P, which is the end of link 5, is not on the arc. That is to say, when it moves from here back around to there. That's the strategy. So I'm going to do an example, and the example I'm going to do will have the requirement that we have an output motion of a rotating link with a total angular displacement of 22 degrees, And we want this to dwell for 90 degrees of input to the constant speed driving crank into the Grashof 4-bar stage. So here's our strategy. This sums up what I just described on those two diagrams. We're going to try a circular arc coupler curve. This I hadn't mentioned before. Symmetrical coupler curves tend to have good pseudo-arcs because arcs are inherently symmetrical. So we'll use symmetrical coupler curves as a means to find our arc-type motion. So the first step in the procedure will be to find a suitable Grashof linkage that has a pseudo-arc in the coupler curve that lasts for at least 90 degrees of crank motion of that linkage. The second step will be to construct the output dyad that generates that required 22 degrees of rotation for this example and also have the required dwell. This is another figure from your book which shows the geometry of a so-called symmetrical coupler curve linkage. And what makes it a symmetrical coupler curve, which by the way is defined as being mirror symmetric about a line from the coupler point when the crank is in this position at 180 degrees back to the fixed pivot of the rocker link. This is a Grashof crank rocker here. It says crank, coupler, rocker, ground link. What makes it a symmetrical curve is the fact that the length of the rocker is the same as the length of the pin-to-pin distance on the coupler, which here is labeled AB, and is also the same as the length B to P, which is the coupler point, this so-called BP vector. So this line, and this line are all the same length. And with that constraint, you'll have a symmetrical coupler curve. This angle gamma, which is measured at the link 4 end of link 3, is another parameter that will determine the shape of the coupler curve. But we can vary gamma over its possible range, and we'll always have a symmetrical curve, provided these link lengths are as described. So we're going to use that trick to find ourselves a curve. Now this table is also in your text. It's figure 321A. And this shows a slice of a three-dimensional matrix of these symmetrical coupler curves. And these were generated by Professor Sridhar Kota of University of Michigan in his PhD thesis that he did at Minnesota quite some years ago now. And this is a handy table that gives us some hint as to what shape curve we can expect with particular ratios. Here are the ratios L3 over L2, L4 over L2, and BP over L2. And if those are all the same, we'll have a symmetrical linkage. This table is for a case where L1 over L2 is a particular ratio, namely 2. In other words, the ground link is twice as long as the crank. And these ratios would apply to all the other three lengths in question. Class 1, you may recall, means it's Grashof. Class 3 would be special case Grashof. I want to avoid the special case. So I'm going to look in this section of this chart, and I'm looking for circular arc type curves. Well, I notice that over here on the left, that looks sort of circular on the back side of that. So does this, so does this, so does this. For that matter, so does that. But this looks like a better candidate. So I'm going to somewhat arbitrarily choose a value 2 here for my common link ratios. L3 will be twice the crank, L4 will be twice the crank, BP will be twice the crank. And that will define my linkage geometry. And then I can play around with the gamma. You'll notice that gamma is the other variable on this axis. And if these two look promising, I could perhaps take a gamma someplace between 36 and 72. So that's how I'm going to get my starting point. So here's the same diagram we saw before, and this is going to record what I'm choosing from that chart that we looked at a moment ago. So my L1 over L2 will be 2, as will all the other ratios of my particular links. And I'm going to choose an L2 of 1.5 inches. And I'm going to choose a gamma of 60 degrees. I should make that choice somewhat arbitrarily. That will give me an equilateral triangle, which will be itself symmetrical in the coupler plane. That is, it will look like this, with an angle of 60 degrees in the corner. So let's do that. I'm going to take this linkage dimension information into program 4-bar, which I'll do now, and type in those data. So here I am in program 4-bar. I've already done this to save some time. So we have my 1.5 inch crank, 3 inches for all the other links, link 3, link 4, and link 1 is at 3 inches long down here. And the distance to the coupler point is also 3 inches, and I've got an angle of 60 degrees. Now you might wonder why it's minus 60. I'll show you that in a second. All right, so here's the linkage. And I can articulate that linkage in the program. I can move that around so see that that does go around the curve. In fact, I can go to the animate screen and I can run this. If you've played with this program or seen the tape on 4-bar, you should know how to use this. So here is my circle arc, my pseudo arc, if you will, is on the back side of this curve. And that's the portion I'm going to use. And I said that I wanted to have 90 degrees worth of dwell. Well, I'm starting here at minus 45, and if I run that minus 45 to 0, and then up to plus 45, if you look at this number down here, you see where I am at theta 2. So I'm going to go one more increment to 45. So from there to the start point looks pretty much like a circle arc. So I'm going to try this curve and see what I can make of it. So my next step then, having satisfied myself that this looks like what I want, is I printed this out. And to do that, I did an Alt print screen key combo, and I pasted it into Microsoft Word, and then I printed that out, and I took it to a Xerox machine, and I blew it up 3 or 4 times in order to get it to a size that I could work on. So that's what I have in front of me on this piece of paper. So what I've done is made a copy of that screen, cut away the stuff that was not of interest, and shown it in an arbitrary position. So here is my crank, link 2. Let's label that as such. Here is my coupler, link 3. Here is my rocker, link 4 over here. And here's my coupler point, which I think was called P. Let's put a P on that. And I think this was called A, and this was called B in those diagrams that we looked at a moment ago. And here's my coupler curve, and I've put the coupler curve points on in the diagram. I didn't do that when I ran 4-bar, but it's just a switch that you can turn on to draw these little circles, and those are at every 5 degrees. The little line indicates the angle of the coupler at that point, which I don't really care about at this point. Okay, so it turns out that 0 degrees on the crank happens to be here at this point. And I'm going to label these minus 5, minus 10. Oh, I'm sorry. I'm remembering wrong. I did these every 10 degrees, not every 5 degrees. So that's minus 10. And that's minus 20. And that's minus 30, minus 40, and minus 50. And going the other way, it's 10, 20, 30, 40, and 50. And I'm looking for 90 degrees worth of dwell. So that means I want to go from somewhere there, plus 45 to minus 45 around that point. And that's the piece that I want to be my arc that will cause the other end of a link that I'm going to create in a minute to be essentially stationary. So what I want to do is find the center of this approximate arc. Now you may recall that it's very easy to find the center of an arc if you can construct some perpendicular bisectors. So what I'm going to do is draw a couple of chords. And to get some reasonable accuracy, I'm going to go from the 0 degree to the 40 degree crank angle there. And I'll do the same on the other side. Go from the 0 to the 40. So now what I've done is constructed chords along the arc. And now with a compass, I can draw perpendicular bisectors of each of these lines. And when I extend those bisectors, their intersection is going to be the center of at least that arc, if it is truly an arc. So I'm going to set this compass to an arbitrary radius as long as it's larger than half. I'm going to go up around 35-ish. And I'm just going to draw a circle, because I need the arcs on both sides. So just draw a circle there. Now without changing the radius, I'm going to go to the other end, to the 40 end, and draw another arc. And I'll go down to the minus 40 end down here. Oops, I changed the radius. I got to reset my radius. I bumped the compass. Okay, there it is. This 15-cent compass doesn't hold its radius terribly well. Okay, there's my construction for the perpendicular bisectors. Now with a straight edge I can draw a line which is the bisector through the intersection of those two arcs. I'm using high school geometry here, nothing more than that. We'll extend that. We'll do the same over here for the other guy. And we'll extend that until it intersects. So this is what purports to be the center of that arc. Now let's check that with my compass. If I put my compass point at this point that we just constructed, and I set its radius to, we'll just take one of these points. So let's take the middle guy, since that was where we started. Take the 0. So I get my hand out of the way so you can see what I'm doing. So I'm setting my compass radius with the point over here in my new center. And I'm going to draw that along here to show you that it's not too bad a fit to that coupler curve that lies under it. I can see a little bit of error up there approaching the 40, and maybe a little bit of error down here at the 40. But that's a pretty good approximation. For engineering purposes, it's not too bad. Let me draw it a little darker so you can see it, because it doesn't contrast well with the black line beneath it, and in fact it's sitting right on top of that black line for most of its duration. Okay, so I'm satisfied that this is a reasonable arc center for this particular piece of arc, and I'm interested in the 90 degrees worth of it from there to there. So I'm going to put a link there, and I'm going to draw it connecting where P happens to be drawn, right here, to here. So these are going to be pins, and I'll just have to freehand it here. We'll put a little radius on the end of the link up there and down here, and I'll use a straight edge to connect them so they won't look so crooked as if I did it freehand. So there is what I'm going to call link 5. Okay. Now you recognize that this point P is part of link 3. It's the tip of that triangular coupler. This is 3 right here. So I've just connected a new link 5, as I've numbered it, to link 3 at that point, making a joint. This is going to give me a Stephenson's type mechanism because I'm connecting to the coupler. All right, now the remaining task here is to determine what happens to this other end. I think I called that D. We called that P. Let's label this D down here in the other screens. What happens to D when this end of link 5 takes a trip around the coupler curve? Well, this link is whatever length it is, which is in fact the radius, isn't it, that we just set it to. So if I let my compass now represent link 5, and I follow, let's go the other way, if I follow the coupler curve around, I could draw little arcs over here to get an idea how far it goes. Of course, it could be anywhere on that arc that I'm drawing, couldn't it? But my strategy here is to let the other extreme end of D's position be more or less along a line that splits this angle that I created to determine D. So without further ado, let me draw that line in. You have to make arbitrary decisions when you design linkages because you have too many variables to begin with. You don't have enough equations to solve for all the variables. So you're making assumptions. You're making guesses, essentially. So I'll explain why I do it in this particular fashion before I'm done. But I'm going to want D to stay more or less close to that line that I just drew here. So that will mean that when I'm at this point over here, when P has come all the way around to here, D would be here on that line, wouldn't it? And if it were here, it would be there, which is a little bit shy of this position. And let's go over to here. And that's further back. So this, I propose to you, is about the extreme excursion of D if I cause it to go more or less in that direction. So let me put a circle around that as well. And a little tick mark. I'm going to call that D prime. So that's the later position of D, but I have to control that end of D, and that's where my second link of the dyad, or sixth link of the linkage, comes in. So what I'm going to do now is do another perpendicular bisector business. I'm going to bisect D prime and draw a line perpendicular to it. So I'm going to set the compass to some arbitrary radius, if it will please stay there. I do have a better compass than this, but I couldn't find it today. So I'm reduced to using this dime store version, which is not the most accurate tool in the world, but I think we can make it work. So there is my perpendicular bisector approximately. Now I could draw this either upward or downward, and I could make this thing work, but I have more paper upward, so I think I'll go that way. Now, what I want to do is create another link. I'm going to let my pencil represent the link to give you a little hint as to what's to come here. And if I pivot this pencil up here and cause the other end to be connected to D and link 5, this pencil is going to be link 6. I think you can appreciate that this pencil will eventually swing over to D prime and then back again as P goes around that curve. And the real magic of this is that while P is traversing this arc portion, arc in quotes, D will be essentially stationary. So that will be my dwell. So this link should stay pretty much stationary here. And once I get off that arc and start to come around the corner, it's going to go fairly rapidly over to there and then back again. So the other piece of the problem statement that I chose for this was that this output link, which is the one I'm representing with the pencil, should go through an angle of 22 degrees. So how do I figure that out? Well, it means I want to pick a pivot up here someplace that will, perhaps you could zoom out a little bit and I can show them that a little bit better, because my pivot's going to be up here. So I want to pick a pivot such that this angle that I'm rotating this through is 22 degrees. Well, I can use a little trigonometry to figure that out. So if I go to my diagram here and measure the distance from D to D prime, which, by the way, should be obvious is the same as the distance across the curve up there, because how did I get that? I put my compass at the other end and drew the same length down to here. But either place you measure it, you'll get the same result. I get about 1.8 inches. So I'm going to record that up here. D prime is equal to 1.8 inches. Now let me draw a little diagram offline here. I'm trying to find a pivot up here someplace. And I want that pivot to be such that this represents D and this is D prime, such that this angle right here is 22 degrees, which means that this angle, the half angle, is obviously 11 degrees, yes? Let's darken that in a little bit. I know that this distance is 1.8 inches. I just measured it. This is the perpendicular bisector, so this distance in here is 0.9 inches approximately. So I can solve this triangle. I want to find this distance, let me call it y arbitrarily, and I can get that from the tangent of 11 degrees. So y is going to be equal to this leg, 0.9, divided by the tangent of 11 degrees. And if I punch up my calculator, I'm going to find out that the tangent of 11 degrees is 0.1944. and that gives me a y of 4.63 inches approximately to do decimal places, which is about the best accuracy I can do with a ruler of this sort. So that's about 4 5/8, so I'll call it that. So if I put my ruler on my perpendicular bisector now, there's 4 5/8, and I strike that off, I now have a fixed pivot for link 6, which I'll represent with that notation. And I can now draw my link 6 in this position. It's going to be fastened down here to link 5 at D. Again, I'll have to freehand the end of it here. Actually, I don't think I want to end it there. I want to extend it, so I'll change that in a second. Down to here and back up to there. Now, actually, you might want to extend this guy up here someplace. To let this be the end effector, I can let that be my link that does the work, if you will. But now, let's see what happens. This link 6, let me label that 6, is going to swing from here to D prime over here. Let's draw that a little bit further. It's actually shown in one extreme position. So it's going to go through this 22 degrees that the problem statement asked for. At this point, I have my linkage design. All I have to do is grab some other data from it. I need to know where this pivot, which we're going to call 06, is, because that has come out in the wash in the process of this construction. So I can just take my rule and sit it on here and read that off. Gee, it happens to be 4 5/8. That's interesting. I didn't plan it that way, but that's just about what it came out. So here we have an x dimension. I'll sneak that in over here. So 06x I make to be 4.625 or thereabouts to ruler accuracy. Actually, that should be minus, shouldn't it? Because I'm going to the left. I should label these. I'm going to make this my XY origin down here. The crank pivot is where I typically want to stick the global origin. And I need now to have the Y offset for that. So we'll just extend my x-axis over here and put the ruler on it again. And that's about 4.5. So 4.5 inches. So that I would call 06Y, and that's positive. So it's to the left 4.625 and up 4.5 to that pivot. Now I need the link length as well. This link length of link 5 turns out to be pretty close to 4.25 inches. Let's call it that. So that's 4.25 inches. And we already figured out the length of this guy, I think, did we not? No, we didn't get that. We got the Y dimension. So this guy is pretty close to 4 3/4. Let's call it 4 3/4. 4.75. Okay, so I have my linkage now, and I can record those data, and I can now make a model of this, which I've done. So let me show you the model, and then after we've looked at that, I'll show you how to get the data into program 6-bar, and you'll be able to articulate it there as well. All right, so here I have at least an approximate model, as best as can be done in cardboard. Here's the original 4-bar. There's link 1 taped down to the page. Here's link 4 over here, pivoted there. Here's link 3, which is my equilateral triangle. Here's link 2, which is the drive crank. And here's the coupler curve being generated by that. If I can avoid stubbing toes, I can get it to go through the whole thing here. And let's put it more or less where it was in the previous picture. I had this up in this neighborhood. So here is my link 5, which has its other end at the approximate center of this piece of arc, which I've labeled C over here. Now watch this point as I move this through the arc. And you'll see that it does not move very much. It's not dead still, because, again, this is not an exact arc. So there's a little bit of motion. But now as it comes around the corner, notice that it moves a lot, and that takes link 6, which is this guy over here, from its original position where it was dwelling over to here, where you see the mark. I'll do that again. So if you focus your attention on link 6, if you look at it with respect to those dots, it should be moving, if I can do this without stubbing toes. Now it's over at the dwell position, and it should be staying fairly still because I'm on the curved part, the arc part of the coupler curve. And now it should start back in its motion. It's at the extreme about there. Dwell, move, dwell, move, dwell, move, stub your toe, dwell, move, etc. Okay? So that should give you a little sense of what we have created in the form of this dwell mechanism. Some disadvantages of this approach as opposed to a cam and follower are that A, it's not an exact dwell. B, to get this little bit of 22-degree motion over here, I have a fairly big package of fairly long links, so it may be difficult to package this. A cam and follower, to make this thing move through 22 degrees, could be quite compact. I could have a cam about the size of this bottom of link 4 driving directly against a roller on link 6, for example, and make it go through that motion and have exact dwell at one position. The trade-off there would be I would gain the small package size, but I would now have an open joint in the form of a cam follower joint, which requires lubrication, is somewhat difficult to lubricate, may have some wear issues. I might have follower jump issues, etc. Nothing is free in engineering. Everything that you gain comes with some kind of a penalty. So that should give you some idea of how this works. Now I'm going to move over back to the computer and go to 6 bar. And I've earlier put into program 6 bar the dimensions that we generated. This is the 4 bar stage here, the 1.5-3-3-3, with the coupler point at 3. And these are the link 5 dimensions, or approximately what I just did. I actually constructed this earlier, and I got a slightly different length for link 5 at 4.15. But this will give you the idea. So if I calculate this, in fact, if I go to the animate screen, you can see it better. I can now move this through its motions, just as I did with the model. And here, let's just start at the beginning over here. This is going from minus 45 to 315 on the crank. That's more or less how I set it up on the construction sheet. So as I move this through, I'm on the arc, and you can see this point, which is what I labeled D, is not moving very much until I get about there. Now I'm at about 45. I am exactly at 45 positive. So I'm at the end of my pseudo arc. Now it starts to move. You'll notice that link 6, which is pivoted up here, is now rotating over to its extreme position, which it happens about there at 180 in this case, and back again. So if I'm going to run that so you can see this. Let's actually make it cycle more than once. Go around 5 times, maybe slow it down a bit. There. Actually, let's slow it down even more. It'll be easier to see. Now, you watch that. You can see the hesitation when link 6 gets over to this right-hand side. Make it 10 revolutions. So when it gets to this position, you can see it hesitate, and that should dwell. So I hope that gives you some idea as to how to construct a dwell mechanism, at least of this variety. It's called a single dwell. It's possible also to create double dwell motions. I show you how to do that in the book. Requires a curve with 2 circle arc pieces. Or there are some alternative methods using straight line sections of curves. In any event, this should give you some idea as to how to approach that design problem. Thank you.